and other magneto device. So, but here I want to say that the initial band structure calculation can actually play a very important role by revealing the mechanism, but also help experiment people to search for a new spintronic material. And the recent intensive research on spin Hall effect also led us to the creation of new hot topics such as topological insulate and the spin characteristic. Now, finally, I needed to thank many people, including Chen Liu and Yao Yigui, his postdoc, and my student, now he's in Songyeseng University, and also colleague, Professor Chen Liangfang and his experimental team, and Japanese scientists Nakaosa, Murakami, Mayakawa, and also Gubo, and very importantly, our National Science Council for funding. And finally, for your attention.
Let's thank Guan Yu for giving us such a very interesting talk and review of the development of the spintronics. And I have to be honest, this is the first time I feel the theoretic talk can be so interesting and really it's related to what we are doing. Okay. Any question? Yeah.
You mentioned you will get the equations of motion that is more symmetric after you add the very phase term. Is there a profound symmetry reason behind it, or just the equations just look more symmetric, but theirs actually is not as symmetric?
I do not know very deep theoretical framework why these two equations should look so symmetric and beautiful. But that's the basic instinct of Liu Qian and Zhang Minze. So, but they happen to be working on Berry phase effect on transport for many, many years. But then they come across this problem and sorry, they might be disappointed.
You mentioned that in one of the introduction remarks about the spintronics effect and magnitude device, then you can solve at least NTU physics.
By the time he may step down already.
But what kind of device that you're talking about then can replace the present CMOS?
Yeah, I think you probably know better answer than me. You are experimenters and you're working on 5nm technology. But anyway, so far I only found that group, what called Lumen, or you probably know that who published science paper. Yeah, maybe Su Yan also know better than I do. But that's even though only one, but that's a very important application. Let me maybe go back. Somehow my remote control is not working. Actually, which one? Yeah, this one. So I think this this would be very good. This is TMR junction. Okay, which I think in the previous our colloquium, Su Yan also mentioned about that, and this can be a very important element in this new magnetic memory technology.
Of course, spintronics already have a device in memory devices.
Yeah, that's not all. Yeah.
I think it's more important than looking beyond. CMOS, right?
Yeah.
5 nano. So what happens next?
It's not expensive.
Yeah.
No, I encourage you to jump out of your box and think about more reality, not just 10 machine
Yeah.
home.
No. To me, it's very realistic already. Okay, don't push too far. I have a question about this condo effect. When you first see this when first experiment, you got this very large, spin hole conductivity, right?
Yeah.
But it's only a contamination, right?
Yeah.
So presumably there are very, very few ion atoms, right?
That's right. Yeah.
Right. So this can have such a big effect, and then if you put a lot of how does this conductivity vary with this ion?
The spin Hall angle.
No, if we don't, the spin Hall angle is almost the same.
Yeah.
Because how about the other properties? There should be some property that is concentration dependent, right?
Yeah. This kind of conclusion assume we have dilute impurity.
Okay.
So-called dilute. By dilute, I mean impurity has no interaction, but it still can add more and more impurity. But maybe there's a critical point where impurities start to interact. So in this case, then the conclusion I make cannot be applied. Okay, so that's the critical concentration. Upper limit, I can talk about this kind of spin Hall angle. Yeah.
Yeah.
So in your introduction, say the traditional Hall effect, you show the E plus E minus, they go to different sides.
Yeah.
Due to Lorentz force law, but I saw it's the same side, right? Then we can tell what's the majority carrier. No.
Well, that's an important technique our chairman used, and Professor Cheng and everybody using in semiconductor to determine carrier concentration and type of carrier. Let me.
I think the second page or something.
Yeah.
Yeah.
So
E plus E minus.
this electron current going that way.
Yeah.
Okay, and the electron going that way, isn't it? Now.
Yes. So the same side, right? So you can tell what's the majority carrier.
You got confused. It's the electron and hole. It has a negative.
This is the hole going that way. But okay. I see what you mean. Yeah. If we assume only one type of carrier, so the sign of this Hall coefficient will depend on the sign of charge of carrier. Yeah, but of course I did not say how it's dependent on that. Well, he knows better than me. Yeah. So now this I understand it's very important technique to determine carrier concentration, also type of carrier.
If you have an electron accumulation on one side, right? Because of charge balance, you have to have positive charge on the other side. But then, with the same magnetic field, electron will, if the conduction is electron, then this side is a higher voltage than that, and if it is holding.
I mean, this is in general physics course. I remember you also taught about that.
Just want to give you a hard time.
But I was nervous because the previous page I got the sign wrong, and after my talk, some people said that your Lorentz force is wrong.
Thank you for your interesting talk. I have two simple questions. Do we need ion impurity to have a multi-orbital condo effect? Do we need ferromagnetic impurity or normal impurity can also have this orbital condo effect? And second question is, in your calculation, you score with the ion impurity. Both are heavy metal. Recently, people find the light metal doped with heavy metal can have a large spin angle, like copper doped 5.5% of business.
Yeah, you are obviously an expert in the field. The first question is that you do need magnetic impurity. You not necessarily a ferromagnetism, but you need the impurity have local moment. And in order to have multi-orbital condo effect, so you need the valence shell, like a D shell, which is partially filled. So with these two conditions, it might have a multi-orbital contact. Now, the second question is critical. Okay, last semester I took my sabbatical leave, and I spent 2 months with the with the Ingrid Mati group, and she is the one did the calculation you mentioned. Okay, but they have also a story how this giant spin Hall effect occurred. But their theory is that if you dope gold with a light atom, okay, but the potential difference is so huge, because if we have gold, which is big and large and heavy, if you dope with a nitrogen, okay, which is small and tiny. Now, imagine an electron passing through this kind of impurity. You will also feel a very strong scattering potential. So they explain that that's why they're doing first principle calculation with this kind of light element impurity. They also find a giant spin Hall effect. Okay, because I had their slides in my because I want to point out that life is always complicated. But because of time, so I did not put this in. But nevertheless, this can maybe some experimental can deliberately dope with the nitrogen or boron to see whether you can also find giant spin Hall effect. I think this may be open for experimental people to differentiate.
I see that you explained the spin Hall effect by 2 different mechanisms. One is intrinsic, the other extrinsic.
That's right.
So the intrinsic actually, I think, is already constrained by the material.
Yeah.
So in the future, if we want to increase the spin Hall effect, we must, I think, go through the extrinsic mechanism. Is that right?
I'm not sure, but I think intrinsic is more stable, isn't it? Because it's already built in the sample. Another thing is that spin Hall angle for heavy element like platinum, and also some of the system found by Professor Van Siyen. And for tantalum and tungsten, they already have very large spin Hall angle. So they, as demonstrated by this group, I still can't pronounce his name. So they already can use this tantalum to drive magneto device. But if we want to simple, pure metal to drive that, and this is actually better. But to me, impurity concentration may be difficult to control. But I always admire experimenters, they are very smart. Okay, so.
Okay. Okay, this will be the last one. Okay.
The Hall effect gives many Nobel Prize in this field. Maybe this will get another one. From your point of view, why it's so important in physics, or especially in condensed physics, the Hall effect? Thank you. To get a Nobel Prize. Thank you.
My answer or my guess would be spin Hall effect will not get the Nobel Prize, but quantum spin Hall maybe. You know that our Vice President Zhang Qingrui already invited Zhang Shoucheng to be our honorable research chair professor. Okay, because of this quantum spin Hall effect and topological injury, he already got the Dirac medal. Okay, now people speculate if more experimental being carried out on the quantum spin Hall effect. The 3 people, Chao-Qiang Geng, and Zhang Shoucheng might get the Nobel Prize. That's my guess. Don't quote me. Okay.
By the way, Monaco is also our distinguished professor.
Oh, okay.
Okay, so let's thank Guang Yu for his wonderful talk again.